Hello and welcome back to my channel. This is the first video of my distributed training playlist. Today I want to just give a brief introduction into the concepts of data parallel and model parallel. So what we're going to do today is I'll lay out a simple model, which is kind of like a simplified version of transformer for text processing. And then I'll try to come up with what is data parallel from the basic principles, from just looking at the math, just looking at the tensors, how we split them across devices and what it means to be data parallel. And then I'll do the same for model parallel. And so we start with our simple model. So this is an overview of how it works like. So we start with just some sort of input text. Then, as typical for NLP models, we tokenize the input. So we split the input into tokens or words. We look up every token and replace the actual text with token ID. We also add some special tokens. So this one is the CLS token, this one is a padding token, and so on. Then we do what is called embedding lookup, where one integer, one token ID, is getting replaced by an embedding vector. And then we just project that down using dense layer, and then another final layer, and then some pooling to collapse this sequence length into one. So let me show you that in code. So this is how the model looks like in code. So the model itself has just three layers. So embedding layer to convert token IDs to actual embeddings, one hidden layer to do some sort of computation, then the final layer to collapse that down to necessary dimension, and that's it. And then during forward method, as an input, we get input IDs. We apply this embedding, we apply hidden layer, final layer. Then we do what is called pooling to collapse sequence length into one. And then we also have some sort of loss. So it's a weird loss, but whatever. So what it does is it collapses some sort of output, one per example, into a single scalar for entire batch. And you can see here how the actual process of inference look like. So I have two input texts. Just some random texts. I apply the tokenizer. The output of the tokenizer is going to be this list of token actual input IDs, attention mask, and token type IDs. And then I can apply the model to that. I can also do that in a more interactive fashion. So I can just put a breakpoint, click on debug cell, and here I am. So I can see what input IDs are. So it's a tensor with a shape of 2, which is the batch size, and 9, which is the sequence length. So sequence length is basically the number of words in a sentence. And we can see here that first sentence was a bit shorter than the second one. So we get this extra padding token to pad them all to the same size. So then I have my embedding lookup. So embedding itself is, again, a matrix, which basically projects this list of token IDs into an embedding dimension, which is 64 in this case. And this 30K dimension is basically the number of unique tokens, the vocabulary size, the number of unique words that the model is aware of. So when we do this projection, what happens is we basically expand this vector and it gets an extra dimension of embedding. So we had 2 by 9, now we have 2 by 9 by 64. So batch size, sequence length, hidden dimension. And then we do some actual computation. So we apply our first hidden layer. Our first hidden layer is just a dense layer with 64 by 64 kernel. So when we do this model, when we do this call, which is in fact matrix multiplication, what is supposed to happen is we sort of collapse one of these dimensions, one of the common dimensions. But since the second one is also 64, the shapes don't really change. So the output is going to have this shape of 2 by 9 by 64 again. Then I have my final layer. So let's take a look at that shape. So it is now a 64 by 1 kernel. So when I do the multiplication, this dimension collapses and I get 2 by 9 by 1. Okay, so 2 by 9 by 1. Then I do the pooling, so I call torch.mean by the first dimension, meaning that I'm going to take the average across this sequence length dimension. And so the pooled vector is now 2 by 1. Okay, and I also call this squeeze method, which removes this single dimension. And then when I compute the actual loss, I collapse this. So again, I call torch sum. So outputs now is two numbers, one output per element in the batch. And then when I call the loss, I collapse that to a single scalar. So another look at all of this. So what just happened, this basically represents a simplified version of transformer model. So it's not really a transformer because it doesn't really have interaction between sequence element. Instead, this hidden layer basically treats all of them independently, but input and output shapes are quite the same. And finally, it only has one layer, which is good for our case because we just need to understand what is going on there. Another thing that I want to do is just to write down the actual mathematical equation for these matrix multiplications for these layers. So let's start with the first hidden layer. So above we can see how it looks like in code. So hidden layer itself is defined as PyTorch linear layer of dimensions embedding dim times embedding dim. So it's a square matrix. And then as an input, this out1 tensor, we had something with dimensions batch size times sequence length times embedding dimension. And as an output, we have the same shapes. So we call this hidden layer to turn our embeddings variable output of the embedding lookup into this out1 tensor. And so this is how it looks like as a mathematical equation. Basically out1 is itself a tensor with 3 dimensions: batch size, sequence length, and hidden dimension. And so it can be represented as basically this variable with 3 indices, where each index basically says, well, which specific place in the tensor you need to look up. And so we have indices B, which stands for batch index, and it goes from 0 to batch size. We have S, which is the index of the element in a sequence, and it goes from 0 to sequence length. And then we have 2 H indices, so H0 and H1, which both go from 0 to embedding dimension, and we have 2 different of them because of this square matrix. So the same embedding dimension is basically represented twice, once in the input, once in the output. And this actual matrix multiplication can be roughly depicted as this equation. So we have this embedding tensor, which is an input. It also has this 3 indices. We multiply that by layer 1, and multiplication here is a simple number multiplication. So after looking up all the indices, this is just a number, this is just a number, and then we sum over all the elements from this H0 index. So we go over all indices in one of these hidden dimensions, and we sum them all up. So what you can see here happening is basically this H0 index, H0 dimension getting collapsed, summed up into something single, right? So in the output, we don't have this H0, but we have H1, which we got from this layer. Let's do the same for another layer. So final layer is a bit simpler. So it's not a square matrix, it's a matrix projecting hidden dimension to 1. And so as an input, we again have this batch size times sequence length times embedding dimension. And then as a result of this multiplication, we get this embedding dimension collapsed to 1. So this is how it looks like as an equation. So again, we have this tensor with 3 indices. We have this kernel of the second layer, which now only gets indexed by this one index, H1, which goes from 0 to hidden size. And so again, we sum over all the elements of H1. So this dimension gets collapsed in a sense. And then the output will not have this H1 dimension. It will only have this B and S. So that's our output. So it's the basically embedding dimension got collapsed to 1. So we have now one number per batch element per sequence element. Now let's do the same for pooling. So pooling just basically collapses this sequence length dimension. Now it doesn't have any parameters, any trainable parameters. So it's just torch.mean call. So out2 is a tensor from the previous slide, which has indices of b and s. And then we do the mean over dimension number 1, which is the sequence length. So we sum everything up as goes from 0 to the sequence length. And this is the sum, but since we want not the sum but the mean, we also divide by this sequence length. And again, you can spot the pattern here. So we do the sum over s, which means that s disappears from dimensions. And so this output tensor will only have b as the dimension. So now it's just one-dimensional vector. And finally, loss. Again, loss does the sum over this batch dimension. So b goes from 0 to batch size. And again, you can see how this b dimension disappears, and we have just a single number as an output. So this is the introduction. Also, as you might notice, I omitted the bias terms, but we'll need these mathematical equations once we actually try to come up with data parallel. Finally, I wanted to say a couple of words about how these tensors contribute to memory consumption, because that will be important later. So we have two main sources, that's model weights, and the consumption of memory is linear with respect to parameter count. And what that usually means is that and param count is usually a multiplication of the number of layers times embedding dimensions squared. So most of the matrices are square matrices in a typical transformer. So this number of parameters in one stage square matrix is embedding dimensions squared. And apart from that, we also have this amplification factor of around 4, because in addition to storing the parameters themselves, we also need to store gradients, and most probably atom momentums, L1 and L2, which get used by the optimizer, and all of that has to be stored in GPU memory. In addition to the model, we also need to store input, output, intermediate data, and that is linear with respect to batch size, linear with respect to embedding dimension, and linear with respect to number of layers. So you can see here that the increase in the model size, in the number of parameters, basically contributes to memory consumption more, because you have this embedding dimension squared, and in intermediate data you only have this embedding dimension, but still that's usually a huge factor in total memory consumption. All right, now we put down the basics. Let's go towards data parallel. So again, I've redrawn the scheme of the model like that. So we have these input IDs, and basically all the gray squares, gray rectangles will represent intermediate data. And then these blue ellipses represent some sort of layers. So embedding lookup, hidden layer, final layer. And then we have these squares, purple squares that represent just operations with no parameters, so pooling and loss. So what is data parallel? Data parallel basically means that we take input data and then split that into n parts and give just a small part to every device, every executor that we have. What that means with respect to tensor shapes is that batch size gets divided by n, and every tensor that had batch size in its dimensions gets split into n parts. So these tensors are input IDs, embeddings, which is output of the embedding lookup, out1, out2, and pooled output. So everything that had batch size gets divided into n parts, and everything that did not have a batch size does not get divided. So we'll see what that means exactly in a minute. So we have the actual embedding matrix in the model. We have hidden layer, we have final layer. All of these don't really have batch size in its dimensions, so they stay as they are. So what that means from the practical perspective is that we had our input data. Let's say we split it into two parts, this yellow part and this red part. and we basically send the corresponding part to each device. And so we can see that input IDs, intermediate output here, here, and here are all independent. So what we have in the red one here does not intersect with what we have in the yellow one here. And all the layers of the model, so embedding layer, hidden layer, final layer, they all get copied around. So this first executor on the top has exactly the same version of the embedding matrix as the one on the bottom. So we basically split the data. We split that into two parts. One goes to one executor, one goes to another executor, and then we copy the model. So we copy each layer into two parts and send each part to corresponding executor. Now let's look at the math again. So let's start with the hidden layer. So this was the equation for the hidden layer. So we have input to the hidden layer, which is the output of embedding lookup, and it has 3 dimensions: batch size, sequence length, and this hidden H0. Then we multiply it by the parameter matrix of our hidden layer, which has 2 indices H0 and H1. And we sum up over all the values of H0, and we get the output. So when we distribute the data into 2 executors, what effectively happens is every tensor that had batch size gets split into 2. And so for one executor, we have index B that goes from 0 to batch size divided by 2. And then for the second executor, we have B that goes from batch size divided by 2 to batch size. So they look at unintersecting indices. Now let's look at this formula again, at this equation. So basically, this equation splits into 2 as well, as long as we copy around this layer 1 here, which does not have the batch dimension. Everything else can be computed independently on these 2 executors. And that works for as long as the sum that we compute here does not include the batch dimension. So every sum, every multiplication that does not include batch dimension is trivially split into n executors, provided that you actually copy around all the parameters that you need for that computation. So the same will happen for final layer, the same will happen for embedding lookup, and for the pooling as well. So what is the place where we actually do get sum or batch dimension? Well, one of those places is the loss. So this is the loss, and here B goes from 0 to batch size, which means that to compute that, we actually need all the variables here that used to be on different executors. We need to pull them into single executor somehow. So this is how the scheme for that looks like. So we basically had what we had before. So we split the data into 2 parts. We pass each piece of data through the model independently on 2 executors. And what we have as an output is basically the loss before we aggregated it across executors. And then to get the final loss, what we do is we call this all reduce. So all reduce is a collective communication operator. And what it does, it basically is it looks at all the executors that are currently working together, all that are part of our training. And it says that we need to exchange the values of the tensor such that every executor gets all the values, they all get summed up, or some sort of custom reduce operator is applied. And basically each executor after this operator is now in sync. So each of them will have this scalar loss, the value of which is exactly the same as for the sum of individual parts. But just the computation of the number, the loss, is not really the most important part. The most important part during training is to actually compute the gradients. So now let's try to use our equations to get the gradient. And let's say we want the gradient with respect to this final layer because it's closer to the loss, so it's going to be easier. And to do that, I basically need to take our loss and perform forward prop through the loss, through the pooling, and compute the gradients of this final layer. I also need to know this input to the final layer to do that. So here is the equation for that. So on the top, I have the actual equation for the loss expressed in terms of input to the final layer and the actual parameters of the final layer. So basically this is the combination of three equations that we had before. So one for the actual matrix multiplication of the final layer. So we multiply the layer with the input and we iterate over this hidden dimension h1. Then I perform the pooling by just taking the mean over sequence dimension. So I get a sum over all the values of s and I divide by this sequence length. And finally, to compute the loss, I just perform the sum over the batch dimension. Now, what is the gradient? The gradient is the partial derivative of this loss with respect to some sort of parameter in this final layer. And I use a different index here, so it's h instead of just h1 to sort of underline the fact that these indices might actually be different. But since the multiplication here is actually quite easy, so this is now just the numbers. And when we do this partial derivative, all of these numbers we can treat as constant, except for this one. And so the partial derivative of this one, again, depends on this index h1. And there are two special cases. So one special case is when h1 is not equal to h. And then we basically, this is the same as computing the partial derivative of x with respect to independent variable y, which is just 0. Easy. And the second special case is when this h1 is equal to h, and this is the same as computing partial derivative of x with respect to x. So these are the only two things you actually need to know about derivatives to come up with this. And this derivative is simply 1. It's quite easy. And so what ends up happening is this entire sum goes away, and it actually contributes non-zero elements only for the special case where h1 is equal to h. And so the rest is just 0. So this entire sum goes away, and we only get this h here. So the partial derivative with respect to h parameter is only non-zero for this h output. And then everything else is a constant, so I just sort of write it out as is. So this is now the equation for partial derivative for the gradient for the final layer. Thanks to the magic of backprop, we can perform something similar for all the other layers, and we can actually do that automatically. But still, let's take a look at this. So you can see here that in here we also have the sum over the batch dimension, which means that it requires some sort of intercommunication between our devices. And this is how it actually looks like. So I don't really need to reduce the loss. I don't really need to send the intermediate values of the loss to other devices unless I want to report some sort of loss value. So what I need to do is I split my input data into two parts. I perform forward pass to get the output. Then I compute the backprop individually on each device. So again, no cross communication here. And I get the values for my gradients. So for three layers: final layer, hidden layer, and embedding lookup. And the values for the gradients will be different on two executors because they're computed using two different parts of the data. But then to do proper gradient descent, I need to synchronize them. So this is where I perform all reduce, which basically means that I'm going to exchange the values of these gradients across all my devices and then sum them all up. And I get my version of the gradient on each of the executor. They're actually going to be equal, but still I have two versions of them, and how it is actually implemented in most of the optimizers is you get this equal values for the gradients, and then each executor applies them independently. All right, we're finally done with the basics, and we can actually discuss what that means. So first of all, we split the input into two parts, which means that we can expect everything to go twice as fast. Or if you use n executors, you can expect it to be n times faster. It's not going to really be n times faster depending on your network and so on, and how much you actually spend on this all reduce communication, which is not needed when you just do a single executor, but still usually it speeds up quite a lot. Another important thing is that this entire call of the model is not modified. This is actually a huge thing with respect to how easy it is to implement. As we'll see later in the playlist, data parallel usually is implemented with just a single wrapper from PyTorch. So you don't really need to modify anything from the model. You can take any third-party model which was not written with distributed training in mind and just use it in distributed context. And that's a huge deal. Finally, the amount of communication needed is quite small, so we only need one all reduce operation at the very end of our gradient descent step when we actually perform the all reduce on all the gradients. So let's repeat all of that. We split into input and all the intermediate data into n parts, which means that we can expect training to be n times faster. Database memory consumption is also reduced by n. That's also a good thing because in many cases you want your batch size to be as high as possible, and that helps with convergence and overall quality of the model that you can get. And so if you have more nodes, more GPUs, you can train better models just by increasing batch size. Finally, the intercommunication is only a single one per batch, which helps you save on this intercommunication time. So it's really an effective algorithm, and no model code changes are needed, which makes it really easy to use. Let's also see what will happen if we increase the size of the models. So first of all, the amount of data that we currently pass around the network, we pass around all the gradients, which is basically proportional to model size. So as the model gets bigger, the amount of data that we send around gets bigger as well, and the complexity is linear. So the effectiveness of communication will go down because we send more data on each step. And at some point, simply the model will get too big to fit into a batch size of 1 on a device. So at that point, we're basically forced to do other approaches, for example, model parallel. So we've gradually approached model parallel, so now let's see what that is. As before, we basically choose a dimension for the tensor that we're going to split into several parts, and we send those independent parts to the executor. And now we choose the dimension that belongs to the model. In our case, there are actually two of them, so embedding dimension 1 and 2, and I've decided to split only one of them. There's actually some logic on how you can do that, and there are different ways of doing that. And now, for the purpose of just explaining, I chose one of them, and I split that into n parts. And so what we'll have here is that the first embedding lookup layer is actually again copied across devices, because this first embedding dimension is not split, and this corresponding first dimension of the second layer. Then the right dimension of this hidden layer is getting split into n parts, and corresponding to that, the first dimension of the final layer is also split. And then if we look at the data, input IDs get copied around all the devices. Embeddings, since this dimension is not split, again is getting copied around all devices. And then output of the hidden layer is split. Output of the final layer is not split because there's no embedding dimension here, and so is pooled output. Again, no embedding dimension means that it's not split, means that it's copied around all devices. And this is how I'm going to depict that. So those layers that got split into n parts, I will depict these red and yellow circle. Everything else, just the colors that they used to be. So the sums that have this h1 dimension will have to be performed with all reduce, because some of the members of the sum will belong to one executor, some will belong to other executor, and to compute proper version of the output, we will need to communicate between these executors to compute this entire sum. And that will happen for our hidden layer and the final layer. Notice that the gradients don't actually contain this hidden dimension. So in the gradients with respect to the final layer, for example, we have this byte dimension and sequence length dimension. So that means that to compute the gradient, now we don't really need to do any cross communication. And this is how the entire thing will look like. So again, input IDs are copied around all the devices, which means that now I take the data and instead of splitting it, I actually copy it to all my devices. The first embedding lookup, thanks to the choice of the dimension that I decided to split, also gets copied around, and so is this output. And then I have two parts of my hidden layer. And these two parts are computed on each executor independently, and they come up with their own version of this output tensor. But before proceeding to the next computation, I have to perform all reduce to compute the proper full-scale sum and have all these outputs correctly represented in memory before proceeding with the next layer. So the next layer is also split into two parts. So again, I get two versions of the output, I perform all reduce, and I get this correct version of the output here. And everything else doesn't need to be cross-communicated. And so in the end, I will have the gradients. And now the interesting thing. So for the layers that are being held only by this executor, so the hidden layer and the final layer, I don't really need to cross-communicate any gradients because only this executor knows about these parameters. So this executor knows parameters, computes the gradients, applies these gradients, and there is no need to communicate that to anywhere else. The only layer for which we do need to compute the gradients and exchange their values would be this embedding matrix that got copied around. And so for that one, I compute my part of the gradient on every executor, and then I perform all reduce to get the full representation of this embedding matrix. So that was my explanation of how you can do model parallel. I'm sorry that it was a bit nuanced because some layers got split, some layers didn't. Nevertheless, I think it's a good way of doing all of that by hand yourself and just seeing where it leads you. And now we can discuss what that means. So model parallel, we pretty much are required to use that once our model doesn't feed into one GPU memory with batch size of 1. So for LLMs, for models bigger than 10B usually, you would have to use model parallel. The amount of intercommunication needed is now much greater than for data parallel. We need intercommunication pretty much after every matrix multiplication. So, and in a typical transformer, there is like a bunch of them per layer, so like 5 or 6 of them per layer, and there's a lot of layers. So the total amount of synchronization steps per gradient descent step is going to be much greater. So it's basically slower, it's harder to make that work effectively. It also requires change of model code. So remember, in data parallel, we just apply the model forward path and backward path as is without having to modify it, and then we exchange the gradients. Well, now we can't really do that because we have all these intermediate intercommunications within the model itself. Typical model that you'd get from Hugging Face from somewhere else usually is not written with the thought of model parallel distributed training in mind. So in order to use model parallel, you'd usually need your own model framework. So an example of such a framework is NVIDIA's NeMo repository that is used for distributed training that we'll talk about much later in the series. Another curious thing is that now basically we do intercommunication for data. So if you actually split all the model layers across devices, you don't need to copy them, but you need to copy the data. And so in many cases, that's actually beneficial because the data size scales linearly to the number of layers and embedding dimensions, whereas the amount of data you would have to send if you were sending model parameters scales quadratically to embedding dimension, which means that in such a case of big models, model parallel might actually be more effective with respect to amount of data that is being sent around. So this is it for today. This is it for my introduction to data parallel and model parallel. In the next series, in the next videos, we will look at some examples and actually implement our own model and train that with those approaches. There's something that we didn't talk about today. So, for example, the highest end industry frameworks talk about 4D parallelism, that is data parallel, model parallel, pipeline parallel, which is when you apply some layers on one executor and other layers on another executor, and sequence parallel, that is when some elements of the sequence are distributed across different devices. And all of that, basically combination of all of that, allows you to train insanely big models effectively and fast. So I leave that as a further reading. This is not something we'll cover, but just so you know that it exists.